CHEM 100. We're going to do a review today for exam 5 on chapter 9, chemical quantities. And chances are very good that we'll finish it today, which means in the schedule, in fact, in the schedule today is listed as a buffer. And next Thursday was supposed to be the review day. But since we're ready to do the review now, the sooner the better. And I'll probably finish the review today, and then on Thursday, I'll just hang around at the appointed time for 30 minutes or so in case someone wants to zoom in or come to class and get some tutoring on the topics. After that, you can contact me directly in my office. All right. So I've changed the order. Rather than take them in order from 1 and 3 marked, I'm going to start with number 5, and I've got the order listed on the board so I won't get lost. And the reason I'm doing this is because the first ones are more complicated problems than these later ones. I want to ease into it and take them in this order, which should give us some forgiveness. And then we'll make them more complicated as we go and pick up those earlier ones later. All right, so we're going to start with number 5. In the reaction, nitrogen plus hydrogen yields ammonia. How many moles of ammonia would be produced from 1.21 moles of hydrogen and excess nitrogen? So here, the reason I'm starting here is this gives you the balanced equation. You don't have to balance the equation. You don't have to write the equation from the text. So that makes an easier starting point. And this is ammonia. Okay. So the problem gives us 1.21 moles of hydrogen. Olivia is here. You mark your present. You'll probably notice I'm starting out of order. I'm going to take them in order 5, 7, 10, 13, and then go back to 1, 3, and 6. Because 1, 3, and 6, for some reason, are more complicated problems. And I want to start off easier. So we're starting with the Haber-Bosch process where nitrogen and hydrogen are combined to make ammonia. And we're given 1.21 moles of hydrogen and excess nitrogen. So with excess nitrogen, it doesn't matter how much. We don't have to consider any exact amounts here. We just say will all be used up, and the question is how many moles of ammonia will be produced. So the emphasis of this problem is on conversion factor. Where do we get the conversion factor to go from 1.21 moles of hydrogen to moles of ammonia? Right? And that conversion factor is found in the coefficients. So moles of hydrogen, and I leave moles off just for convenience. It's moles divided by moles, so they cancel anyway. And then we want ammonia. So ammonia goes on top, hydrogen goes on the bottom, so we can cancel. And the coefficients, 2 here, 3 here, give us our conversion factor. So we've done all the thinking. The rest isn't just number crunching. 1.21 times 2 divided by 3 is 8.07. So that would be, excuse me. I watched my decimal point. 0.807. There we go. So that would be C. Would be our answer. All right. So we're going to skip 6 for now and move on down to 7. Okay. All right. Iron 3 oxide, and the molar mass is given there, reacts with carbon monoxide according to this equation. Fe2O3 is a solid, reacts with carbon monoxide, was it? Yeah. And yields carbon dioxide plus iron metal. And this one also is a balanced equation. So you don't have to write the compounds from the words, from the names, and you don't have to balance the equation. So it's simpler that way. But the complication that's added for this one is that we're given 185.5 grams of carbon monoxide. Okay. And the question is, reacting with excess iron 3 oxide, how many moles of iron will be produced? So the question is moles of iron. Okay. So the complication that's added here is that we're given mass of carbon monoxide. And remember, you can't move anywhere in an equation, chemical equation, with mass. It has to be moles. So we've got to convert this to moles first. And that's where molar mass comes in. Because this gives us cancellation of grams, leaves us with moles. But we need the molar mass to go with it. And for carbon monoxide, it's given there in the problem, it's 28.0 grams per mole. So you don't even have to calculate it yourself. All right, so we divide that into 185.5, and we get 6.625 moles of carbon monoxide. And notice I kept extra decimal points. Right? This is, well, actually, I didn't keep any extra because this is 4 significant figures, and that's 4. So now we need to convert to moles of iron. And this is where we use the example from our previous problem number 5 and simply cancel carbon monoxide and leave us with iron. And the coefficients tell us the conversion factor. Okay. And this should give us our answer because the question is how many moles. So 6.625 times 2 divided by 3 is 4.417 moles of iron. All right, closest one to that is E. So here we have test taking technique. If you have a multiple choice question and there are no wonky ones like none of the above, 2 of the above, those types. If they're unique answers, in this case, A through E, then you pick the best one. And the best one is E. Okay, that was number 7. All right. Okay, next on our list is number 10. Number 10, here we go. So using the following equation, it appears to be balanced. Ammonia plus oxygen. Or ammonias plus, what was it, 7 oxygens? Yep. Yields what? What type of equation is this? There's oxygen. This is a combustion equation, a combustion reaction. So that means it's also a redox reaction. Nitrogen dioxide, one product, and the other product is water. And that will give an LME. Let's try this one. Okay, what are we given? Well, the question is how many moles of ammonia will be required to produce 11.9 moles of water? So the question is how many moles here will produce 11.9 moles? Actually, this is simpler than the last one we did. You can move anywhere in the equation as long as you have moles, and the conversion factors are always derived from the coefficients. So if we have 11.9 moles of water, just checking myself, then we want to cancel the water and leave us with ammonia. Okay. So 4 for the ammonia and 6 for the water. So 11.9 times 4 divided by 6 is 7.93. 7.93. And the water cancels, leaves us with ammonia. That's how many moles of ammonia will be required to produce 11.9 moles of water in this reaction. All right, 10-13 coming up. There we go. All right. Okay, here's the complication for this one. We're given the reactants and products, but the equation's not balanced. So that's the first thing we have to do. So we have, for this equation, we have let's see, Na2 SiF6. Na2 6. That's a solid. And then we react that with sodium, metal, and that yields silicon solid plus sodium fluoride, which is also a solid. Okay. So this one should be fairly easy to balance because we have single sodium, single silicon here. That means the fluorine is the only problem one. You can set up your budget and balance this one fairly easily. But I'm going to try to do it without the budget. And I'm going to start with the one that's not single. Sodium and silicon we hold till last. Remember, that's one of our rules, one of our tricks. So I'm going to start with fluorine. So if we have 6 fluorine here, right, to make 6 fluorine, now we have 6 sodium. Well, we've already got 2 sodiums here. We only need 4 more sodium. Okay, that makes 6 sodium. And silicon. Do we need to adjust the silicon? No, there's only 1 and 1. So we're balanced. And if you set up your budget, you can do that also. It just takes a little longer. Okay, we're given 3.09 moles of silicon were produced. 3.09 moles of silicon were produced. How many moles of sodium fluoride were also created? Okay, so we want to know whatever we had over here has produced this many moles of silicon. How many moles of sodium fluoride? Well, we can see the ratio is 6:1. So we should have 6 times as much sodium fluoride produced as silicon. Now you can set up your conversion factor if you want, but I'm just going to say 3.09 times 6, and that should be 18.5. Right? Because this is times 6. And that would be A would be our answer. Okay, 13's out. Now we can circle back, as they say, to the first one. This one is going to require methods that we developed for limiting reactant. So now we're at number 1 again. Back up to number 1. This is also requires us to take the names of the elements and compounds and put them into the equation. So calcium metal reacts with oxygen gas. Calcium metal reacts with oxygen gas to form calcium oxide. Is that correct? Yes, 2 minus, 2 plus, 1 and 1 is all we need. All right. So we've written our elements and compounds correctly. Now we have to balance it. Well, you can set up your budget, but I'm going to say that we need 2 oxygens. This is a synthesis reaction. Out of 2 elements, we form a compound. It's very easy to balance these equations. 2 oxygens. Now we need 2 calcium. And we're balanced. So that's the first step. Write the equation correctly, balance it, then look to the problem for at the amounts. 5.66 moles of calcium are reacted with 4 moles of oxygen. Okay? And the number of moles of oxygen left over remaining. So we're going to subtract what was used. And this is what we want, what's left over. So what that's telling me is that oxygen is excess. We didn't even have to determine that this was the excess reactant. This is going to be completely used up. Now, is that correct? Well, for every 2 of these, you need 1 of those. So if we have, I'll put it in a conversion factor formula. If we have that many moles of calcium, we want to find out how many moles of oxygen were used. Then we have a 2 here and a 1 there. That means we divide 5.66 by 2, 2.83 of oxygen were used. So now we know what goes right here, 2.83. So subtract that from 4, and we get 1.17 moles of oxygen remaining. Okay. And that would be A, would be the answer to that one. So there were several steps in this procedure. That's number one. Okay, now we're going to number three. Go. Sodium and water react according to the equation. And we're given the balanced equation. Sodium and water make sodium hydroxide plus hydrogen gas. Okay, so we got 2 sodium plus water yields sodium hydroxide in solution plus hydrogen gas. And let's see, to balance that, we need 2 and 2. 2 here and 2 there. Okay. All right. So what number of moles of hydrogen will be produced? Moles of hydrogen will be produced when 4 moles of sodium is added to 1.2 moles of water. Okay. Now, there are 2 ways to find out. We're given absolute amounts, and we're not told which one is limiting. You can be sure that one of them is limiting. There are 2 ways to approach this. We can look at the ratio 2 to 2 or 1 to 1. So that means for every 1.2 moles of water, we need 1.2 moles of sodium, which means 1.2 moles subtracted from 4 is 2.8 moles of sodium is left over. So this is excess, and this one is limiting. That's one way to do it. The other way is to do the calculation for each one. Assume that this one is completely used up. How many moles of hydrogen would it give you? And assume all 4 moles of sodium are used up. How many moles of hydrogen would that produce with excess water? And then you compare them, and the smallest one defines your limiting reactant. Right? I think we're going to have other problems that use that method. So we'll go with the first one since it's easier, right? We know that this one's going to be limiting. Right? And we know that we're going to have 2.8 moles remain. Now, that's not an answer to the problem. It's just easy to calculate. So now we want to go take all of this water and convert it to hydrogen. Okay, hydrogen's 1, water's 2. So we can do this one in our heads. Let's see, 2 significant figures. Moles of hydrogen will be produced. Okay. That was number 3. We'll do number 6, and then we'll be back on track to do them in numerical order. Let's get 6 done. Here we go. We're given this equation, but it's unbalanced. Fresh marker. We're going to take ethanol, the drinking kind of alcohol, and combust it. We're going to burn it in oxygen and make carbon dioxide and water. So this is number 6, right? So we got ethanol. And we got oxygen. And it's going to make carbon dioxide and water. Oh, they're saying this is gas. That's okay. That's fine. We'll go with that. CO2 plus H2O. Okay. Oop. They're saying this one's liquid now. Okay. All right. First thing we have to do is balance the equation before we can do anything. All right, so this equation is going to be a little more complicated to balance. So let's use the budget method for this one. Carbon, hydrogen, oxygen. So we have 2 carbons here. We have 6 hydrogens, and we have 2 oxygens. And on this side, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. So we're going to hold oxygen to last, and we're going to look at which one needs to be balanced. If oxygen's last, then we could either go hydrogen or carbon. I tend to go carbon in these types of equations where we're taking in this case, a carbohydrate. Well, actually, not strictly speaking, it is carbon, hydrogen, oxygen, which makes it a carbohydrate. But I'm going to start with carbon. So if we put a 2 here, that gives us 2 carbons. That changes 4 plus 1 is 5 oxygen. Okay. Now how about hydrogens? Well, we have 6 hydrogens on this side. We need 6 on this side, so I'll put a 3 here. Right. That makes 6 hydrogen. It also changes the oxygens to 4 plus 3 is 7. Okay. Now we go to the oxygens and we use our fraction trick. 7 halves of that oxygen will give us 7 oxygens. And then we want to whole number coefficients. So we multiply the whole thing through by 2. That puts a 2 here, gets rid of that fraction, puts a 4 here, and a 6 there. Okay, so we use that one up. Now we have a balanced equation. All right, what else are we given? 1.7 grams of ethanol. Okay. Oops. 3 significant figures. And 11.2 grams of oxygen. Okay. How many moles of carbon dioxide are produced? So we want the number of moles of carbon dioxide. First thing we have to do is find out how many moles of each one, because the ratio of oxygen to ethanol is in molar quantities, not in mass quantity. So we have to convert this one to moles. Okay, so we need the molar mass of ethanol. It's not given to us, so we have to calculate it. So that would be, for carbon, would be 2 times 12.01. And for hydrogen, it would be 6 times 1.01, and then 1 oxygen. Okay, so let's add those up. 12.01 times 6.06 plus and 16. So this is 46.08. 46.08 grams per mole divided into 1.7 is 3.689 times 10 to the minus 2 moles of ethanol. That's my abbreviation for ethanol. Okay, while we're here, and we're gonna have to find out which one is limiting, why don't we go ahead and see if all of this is used up, how many moles of carbon dioxide would be produced? So we're gonna go ahead and do the conversion. CO2, so that's a 4, and this is a 2. So we just need to multiply this number times 2. And that's 7.38 rounded off times 10 to the minus 2 moles of CO2. Okay. Now we'll do the same thing with oxygen. We have 11.2 grams of oxygen, and we need to convert it to moles. Right? Oxygen is 16, yeah, to 2 decimal places, but we have 2 of them. So it's the molar mass of oxygen, diatomic oxygen is 32. So we'll divide that into 11.2. And let's see. 30, oops. Oh, 32. Here we go. So this is 3.500 times 10 to the minus 1 moles of oxygen. And then we would convert that to CO2. So we have CO2 is 4 here and 7 there. All right, coefficients. So 4 times and 7 divided is 2.00 times 10 to the minus 1 moles of CO2. Okay, what does that tell us? Compare these two. This one is the smaller number of moles of carbon dioxide, which means that ethanol is limiting. 1.7 grams is not enough to consume all the oxygen. So we use all of this up, it makes that much carbon dioxide, and there's your answer. That's in standard notation, so let's move the decimal. There you go. 0.074, 0.0738. Yeah, 3 significant figures. So the answer is E. Okay, that took several steps. You have to be very methodical about it. Okay, now we're back on track. Just as a reminder, what are we doing? There's a one-word answer for what we're doing here. Everything we're doing is called stoichiometry. We already did 7, I believe. Yeah, we did 7 already. We also did 10. We did 13. I shouldn't have erased them. So let's see. The next one I have marked is 18. Okay. How many atoms of aluminum can be produced by the decomposition of 31.5 grams of aluminum oxide? Okay, we're going to decompose aluminum oxide. So you have to understand what decomposition means. We're going to make elements out of this compound. So we have aluminum, metal, and what is oxygen in standard conditions? Standard temperature and pressure, oxygen will be O2. If you don't remember that, then you cannot answer this question. All right, now we have to balance the equation. Well, since we've got elements on that side, it should be fairly easy. We need 2 aluminum, and we need 3 oxygen. So if we do 3 halves, That will give us 3 oxygens. Okay. So now we need to multiply by 2. And our equation now is 2 aluminum oxide yields 4 aluminum and 3 diatomic oxygens. Okay. Now we have our balanced equation. We start with 31.5 grams. Okay. And the question is, how many atoms of aluminum can be produced? So we want atoms here. Okay. We need to know how many moles this is. So that means molar mass, aluminum oxide. So aluminum is 2698. So 2 times 26.98 grams per mole. And 3 oxygens, 16. Let's add those up. And that's 5396. So I divide that into 31.5 and I get, nope, it's not right. That is not right. 31.5, 53.96. Hold on a second. I think this is wrong. Let's try that again. 26.98 times 2. Yeah, that's wrong. And then 3 times 16 is 48. Yeah, that's better. 155.93 grams per mole. Yeah. And the answer didn't make sense. So that's when you stop and check yourself. Now we divide this into 31.5. And that gives us 0.2020 moles of aluminum oxide. Okay. The ratio between the two is 4:2. Right? So you can solve this problem 2 different ways. You can use a conversion factor. Like that. This would be 4. This would be 2. Okay. And that would be 2 times this value would be 0 times 2 is 0.404. Yeah, 3 significant figures. Well, that's how many moles of aluminum. The other way is just to recognize that if you have 0.2 moles of aluminum oxide, for every 1 mole of aluminum oxide, you have 2 moles of aluminum. So it's going to be 2 times that value. Either way works. But the question was atoms. So we have 1 more conversion to go. And you have to remember this one. Avogadro's number. Okay. 6.022 times 10 to the 23rd. And that's 1.22 times 10 to the 23rd atoms of aluminum. Let's see. Well, it doesn't like my answer. Let's see, where did I go wrong? Let's see. This is correct, 31.5. I know the equation is balanced correctly. 31.5 grams. We did this calculation correctly. That's about 50, 48, 26.98 enter 2 times and 48. Well, now that's wrong. And I ended up with that one. So I found my error, 1.0196 divided into 31.5 is, that's still 2, is 3089. So 2 times that is 0.618. Now 0.618 times 6.022, that's 0.23. That's 3.72 times 10. Okay. All right, so if I hadn't corrected myself, I probably would have answered B, and that would have been wrong. So this calculation is very important. All right, that's 18. I'm gonna skip a few, repetition. Go down to 23. Calculate the mass of water produced when 9.47 grams of methane reacts with an excess of oxygen in the following unbalanced equation. Okay, so we got a balanced equation, but they've given it to us as is. We're going to combust methane and produce carbon dioxide and water. They want it to be liquid or gas? They want it to be gas. Okay. So we have to balance this equation. This one should be easily balanced without the budget, but to be safe, I'm going to use a budget. Okay, 1 carbon for those, 2 of those. This is 1 carbon, 2 of these, and 3 of these. Okay. Carbon's already good, so we'll go to hydrogen. We have to leave oxygen till last. So if we want 4 hydrogens on that side, we'll put a 2 here. That'll make 4 hydrogens. And 2 plus 2 is 4 oxygens. Okay. So now to get 4 oxygens, we just need a 2 here. Okay, very simple. So now with our balanced equation, let's see what else the problem gives us. 9.47 grams of methane. And I believe they told us excess oxygen. So we're burning methane in air. There's plenty of oxygen there. The mass of water produced. So we want grams of water. Okay, we got to find out the molar mass of methane, which should be 12.01 for 1 carbon and 4.04 for the hydrogens. 1605. So let's divide that into 9.47, and I get 0.590 moles of methane. Now we want to convert it to water. So methane is 1 coefficient and water is 2. So that would be 1.18 moles of water. Now we want to convert water back to grams. So what's the molar mass of water? We've done that so many times. is 18.02 grams per mole. So that's 21.3 grams of water. That would be E. All right, number 26. Unbalanced equation. Aluminum carbide plus water. Aluminum carbide plus water. Aluminum carbide plus water yields aluminum hydroxide plus what? Methane. Now, is that balanced? No, it's not. 4 aluminum, 1 aluminum. So we need to balance this equation. Aluminum, carbon, hydrogen, and oxygen. We got 4 aluminum, 3 carbon, 2 hydrogen, 1 oxygen. On this side we have 1 aluminum, 1 carbon, hydrogens. All right, we have 4 here, but how many hydrogens here? We have 3. So that's 7 hydrogens. And oxygens, we have 3. Okay. We don't have any elements that we hold till the end. So let's see. We start with aluminum. Okay. Or start with carbon. I'm tempted to start with carbon rather than aluminum. Let's start with carbon. I just have a feeling that carbon's going to work better. We put a 3 here. That makes 3 carbons. Now that changes 3 carbons. 12 hydrogens plus 3 is 15 hydrogens. All right. 3 times 4 is 12 plus 3 is 15. Okay. Now we can go to aluminum and say 4 aluminum here. All right, that makes 4. Carbons are the same, hydrogens. So 4 times 3 is 12. 12 hydrogens plus 12 hydrogens is 24. Oops. 24 hydrogens. We also changed the oxygens to 4. Okay. Now, let's see. No, that's not right. We changed the oxygens to 12. Because 3 times 4 is 12. Okay. All right. Now, something you may not notice is the ratio. 24 to 12 is 2 to 1. 2 to 1. So if we just simply put a 12 in front here, that's 12 hydrogens. Excuse me, that's 24 hydrogens and 12 oxygens. 12, 24, 3, and 4. Now we're balanced. So got a balanced equation. That's kind of puny. Let me fix that. There we go. Balanced equation. How many moles of water are needed? Moles of water are needed to react with 206 grams of aluminum carbide. 206 grams of aluminum carbide. Okay, so we need the molar mass of aluminum carbide. 4 times aluminum, which is 2698. And then 3 carbons. Let's see if I can get this one right. 26.98 times 4. Okay. And then 12.01 times 3 is 3603, and then plus. So I get 143.95 grams per mole. It's about 100. That's about, yeah, that looks good. So we have 206 grams of aluminum carbide. We want to find out how many moles that is. Divide that into 206. And I get 1.431 moles of aluminum carbide. And then we convert it to moles of water by aluminum carbide on the bottom, water on the top. So these cancel. This is 12, that's 1. So I just multiply 12 times that one, and I get 3 significant figures is 17.2 moles of water. Okay. All right, next. Number 29. Okay. Oh, okay. I added one in there. So I think we got time. We'll do 29, and then we'll do that extra one I stuck in there. This may not be on your review document. I don't think it is. Number 29. Consider the following reaction where X represents an unknown element, 6X solid plus 2 diborane. No, that's not diborane. Diboron trioxide. So we have 6X solid plus 2 diboron trioxide, which is also a solid. Yields tetraboron tri-X. Okay. Plus 3XO2. Okay. And I assume that's balanced. Let's check. Let's see. 2, 6. Yes, that's balanced. 165 grams of X reacts completely with diboron trioxide to produce 2.29 moles of B4X3. 2.29 moles. Okay. What's the identity of X? Okay. Remember how you find the identity of an element. You have 2 choices. The atomic number, and I don't think we can get that from this data. That's the number of protons. Or the atomic mass. And we probably can get that from here, because the atomic mass, or the molar mass of an element, is mass per mole. Right? We got the mass. We just need to find out how many moles that represents. Then we can calculate the molar mass and go to the periodic table. So how do we do that? Well, let's see. We know 2.29 moles here, and this is a balanced equation. So we can find out how many moles this is, right? 2.29 mole of B4X3. And we use our coefficients to find out what X is. This is 6 and that's 1. So 6 times that value should be the number of moles of X, which is 13.74 moles of X. Okay, so we have mass per mole. All right, let's divide that. That's 12.01 grams per mole. So you go to the periodic table and you go from upper left and across and down. They get bigger. And we keep going until we find one that's close to this, and it turns out to be carbon. Okay. All right. So let's take a look at that extra one I threw in there. We have X plus 3 fluorine. X plus 3 fluorine yields what? XF6. Okay. We're given 235.2 grams of X. Okay. And XF6 is 347.9 grams. 347.9 grams. Okay, what's X? Well, again, we got the mass. 235.2 grams. Now we need the moles. All right. Remember Lavoisier's law of conservation of mass. This total mass must be the summation of that mass plus this mass. Okay. We can find out what the mass here is by just subtracting that one from this one. $35.2. So 347.9, 235.2 subtracted from it is 112.7 grams. 112.7 grams. Now we can find out how many moles of fluorine. We just need the molar mass of fluorine. Well, 1 fluorine is 19, so 2 is 38. So we divide 38 into that, and we get 2.97 moles of fluorine. So now the ratio is 3 to 1. Okay. Fluorine on the bottom is 3, and 1X on the top. So we just divide this by 3, and we get 0.989 moles of X. 0.989 moles. Divided into 235.2. And I get 237.91 grams per mole. And we go to our periodic table and we keep going until we find 237.91. The closest one to that is uranium. Okay. It wasn't exact, but it was the closest one we could find. So within experimental error, we're saying that X is uranium. And this product is uranium hexafluoride. Right, I'm 32. Which of the following reaction mixtures would produce the greatest amount of product? Assuming all went to completion, each involves the reaction symbolized by this equation. All right, so we'll get the Haber-Bosch equation again. N2 plus 3H2 yields 2NH3. And they're all gases. I left the gas part out. So each of the reactions symbolized by the greatest amount of product. So we want the maximum amount of ammonia produced from these reactions. Okay, so let's do it like this: A, B, C, D. So A is 1 mole of nitrogen and 3 moles of hydrogen. Okay, B is 5 and 3. C is same amount. All the same. Okay. D is 1 and 6. 1 and 6. And E is 3 and 3. Okay. So if we have 1 and 3, what does that mean? 1 and 3. This is stoichiometric. Ratio. So 1 of these and 3 of these will make 2 of those. So that would be the outcome for A. This one is 3, and it only needs 1 of these. So we got excess nitrogen. We only need 1 of them. So 3 of these produces 2 of those. 1 of these only needs 3 of those. So in this case, hydrogen is in excess, and we use up all the nitrogen. So 1 of these produces 2 of those. And 3 and 3 is like this one. Hydrogen runs out. We've only used 1 nitrogen to produce 2 moles of ammonia. So our answer is they're all the same. All right. Number 33. This balanced equation. Phosphorus, P4, plus what? Hydrogen. Produces pH 3. That's got to be a gas. Yeah. Okay. Tells us that 5 moles of hydrogen does what? 5 moles of hydrogen. Okay. Well, the first one reacts with 2.5 moles of P4. 6. Let's see. A is cannot. B, D, and E. So for this one, 5 moles would do what? We'll come back to A. Reacts with 2.5 moles of P4. How much P4 would it be? Well, it'd be 5. And then the ratio of 6 to 1. right? So 6 into 5 is 5/6, which is less than 1. Right? It's less than 1. It says reacts with 2.5 moles of P4. So that's false. How about C? Produces 3.3 moles of pH3. Well, if we do 5 again, and this is hydrogen, and then we have hydrogen on the bottom and pH3 on the top, this would be 4 and this would be 6. So this would be 20 divided by 6, which would be 3.18, 1/3. 3.33 moles of pH3. Yeah, that one's good. Okay. D, produces 10 moles of pH3. Well, it can't produce 3 this way and then run it again and produce 10 moles. Right? We've already calculated what it would produce, so it can't produce 10. Or reacts with 5 moles of pH4. In order to react with 5 moles of pH4, you would have to have 5 times 6, it would have to be 30. You'd need 30 moles of hydrogen, right? So E's wrong. And of course, cannot react with phosphorus, that's wrong. We found the right one. C is the correct answer, according to the balanced equation, stoichiometry. 39. Consider the reaction of magnesium metal with hydrochloric acid to produce magnesium chloride and hydrogen gas. All right, first thing you have to do is write the compounds and balance the equation. So magnesium metal reacts with hydrochloric acid, which would be HCl in aqueous solution, to produce magnesium chloride, right? Yes, and hydrogen gas. There you go. Now, are these written correctly? You take my word for it, and you should know that this is 1 minus, and this is 2 plus, so you need 2 chlorine. Okay, and hydrogen gas must be diatomic. Okay, now we have to balance the equation. Leave hydrogen to last. We got 1 magnesium, 1 magnesium. We need 2 chlorines, 2 chlorines. Now we have 2 hydrogens, 2 hydrogens. That equation is now balanced. If 4.52 mole of magnesium, 4.52 mole of magnesium reacts with 4.52 moles of hydrochloric acid, okay, how many moles of hydrogen gas are produced? Well, we're given an amount of each reactant, so one of them is going to be limiting. The ratio is for every one of these, you need 2 of those. Right? So for one of these, we would need about 9 moles of hydrogen, of hydrochloric acid, which means hydrochloric acid is going to run out. It's not enough of it. So we take this one as our limiting reactant. This is HCl, and we convert HCl to hydrogen. Okay? So we have 2 here and 1 there. Half of that is 2.76, I think, moles of hydrogen. Let's see. Nope, sorry. I tried to do that in my head and it didn't work. 2.22, this is 2, and that's 6. There we go. 2.26 moles of hydrogen. We had to find out the limiting reactant. That makes this excess. Okay. All right, next one. 43. Okay, we're gonna combust nitrogen again. We saw that one earlier. How many molecules of water are produced if 9.12 moles of NO2 is given off? Right. Actually, this is kind of going backwards. I mean, this is a lot simpler than we've done before. Up to this point. How many oxygens? They're all gases, so I'm going to leave the gas off. 7. So we got 4 NO2 plus 6 water. Yep. Okay. So how many molecules of water are produced from 9.12 moles? 9.12 moles of NO2. Well, we do the conversion using coefficients. Until you get the moles of water, you can't calculate the number of molecules of water. So this coefficient is 4 and that one's 6. So 9.12 times 6 divided by 4 is 13.68 moles of water. And then molecules would be Avogadro's number. And let's see, 3 significant figures. Eight 0.24 times 10 to the 24th. Right. Let's see, who's next? Who's next? 45. On time. Okay, looks like we got time. 10,2 fluoride is added to some dental products to help prevent cavities. Manufacturers have to make 10,2 fluoride first, though, before they can add it to their products. Right? So they take 10 hydrofluoric acid and make 10,2 fluoride plus hydrogen gas. How many grams of 10,2 fluoride can be produced from 49.6 grams of hydrogen fluoride? They should have said hydrofluoric acid. If there is plenty of 10 available. So we've got the balanced equation and a lot of fluff. That's why I like to pull things out and put them on the board. Aqueous, this is 2. And aqueous, and then hydrogen. Yes. Okay, so there's our balanced equation, and we're also given 49.6 grams. Check that again. 49.6 grams. How many grams of this are produced? So we need molar mass of hydrogen fluoride in order to convert grams to moles. Remember, because you can't go anywhere with mass, you have to have moles. HF 1.01 and 19. So that's 20.01 grams. Divide that into 49.6. And let's see, I'm gonna keep 2.479. Bet you. Now we can convert that to moles of 10,2 fluoride. Okay. 1 and 2. We'll just take a half of that. And that's 1.239 moles of 10,2 fluoride. Now we want to convert it back. We need a molar mass for 10,2 fluoride. 10 is 118.71. 118.71 grams per mole and 2 fluorines. Right. 156.71. Go. Times. And I get 194 grams of 10,2 fluoride can be produced. All right. Yay. Skip. Must be a lot of repetition. Yeah. Sounds like something I do. Give you lots of practice problems. Number 60. Okay. Consider the following reaction. Okay. This is kind of a generic thing with substituted 2 A's plus a B. Yields 3 C's plus a D. Okay. 3.35 moles of A and 2 moles of B. Okay. React to form 4 moles of C. What is the percent yield of this reaction? Okay. Remember percent yield equals the actual amount of product divided by the theoretical amount times 100. Okay, so the actual amount is 4 moles. But what's the theoretical amount? Well, we're given absolute amounts for 2 reactants. One of them is going to be limiting. So we have to decide which one is the limiting one. If we take 3.35 moles of A and convert it to C, well, actually, we can let's make it easier on ourselves. The ratio between A and B is 2 to 1. So if we had 3.35 moles of A, we would need 6.7 moles of B. Right? If we had 2 moles of B, then we would need 4 moles of A. Let me see. Yeah, 1 to 2. So A is going to run out. Let's do it the other way. It's confusing me, so I'm going to say 3.35 moles of A. Use all that up. Okay. A and C. So this is 3, that's 2. So 3.35 enter, and 3 times into divided. So this is 5.03 moles of C. And then take 2 moles of B and convert B to C. This would still be 3 and this would be 1. So that would be 6. C. Okay, so we know that A is the limiting one. And we produce 5.03 moles. This is the theoretical. That's theoretical. So that would go in the bottom. We would have 4 divided by 5.03 times 100 equals what? 79.5% yield. Closest one to that is D, 79.6. Okay. Right. That was number 60. $61. Calculate the molecules of oxygen required to react with 25 grams of sulfur in the following reaction. Okay. So we have 2 sulfur and 3 oxygen. Yep, 2 sulfur plus 3 oxygens yields sulfur trioxide. Okay. And we're starting off with 25 grams of sulfur. Sulfur in the following reaction. And we want to know how many molecules of oxygen are required. Okay. So we got to convert sulfur to moles before we can do anything. Molar mass of sulfur is 3207. Divide that into 25. And I get 0.7795 moles of sulfur. Convert that to oxygen. Right, so we have 2 here, 3 there. And I get 1.169 moles of oxygen. Now we convert that to molecules. Avogadro's number. And that's 7.04 and oops. 10 to the 23 molecule of oxygen. Okay. At 61. Let's see, who's next? 69. In the reaction between carbon monoxide and Fe3O4. The reason I said Fe3O4 is because the charge on the iron would be a fractional number. And I'll show you why that is in just a second. So carbon monoxide is reacted with Fe3O4 to produce what? Oh, to produce iron as one of its products. Okay, we don't need to know the whole reaction because we're given the theoretical yield is 47.2 grams. And the actual yield is 37. So we can calculate percent yield from these numbers. $78.4. Good. Now, the reason you get, notice if we try to calculate the charge on the iron, this is 2 minus, so that's 8. That's a -8 for this oxygens. Well, we need a +8 over here, but each one then would be 8/3. Right? That's a fraction. Here's the reality. This is a bona fide formula for a mineral. But in order to reconcile charges, we need FeO along with Fe2O3. Okay, so you got equal amounts of each one of these. This one, of course, would be a 2+, and this one would be a 3+. Okay. But you can still write the reaction with that compound. Okay, 69. It's like 70 coming up here. 70. 3.1 mole sample of KClO3. KClO3 does what? Decompose according to this reaction. Okay. I need 3 of those. How many moles of O2 are formed, assuming 100% yield? So with 3.1 moles of this, okay, actually these are simpler problems than some that we've done before. This would be converted by KClO3 to O2. That would be 3, this would be 2. So let's see, that would be, I'll try to do that one in my head. That would be 4.7, rounded off 2 significant figures. Moles of oxygen. Okay. Probably should have come down to these first and then gone back. But too late for that. $71. When 3.4 moles of iron reacts with chlorine according to this reaction, how many moles of chlorine are required to react with all the iron? All right, so we have 2 irons and 3 chlorines. Yields iron 3 chloride. Okay, 3.4 moles of iron. And the question is, how many moles of that? So this should be fairly simple, straightforward. That's iron. We want to convert iron to chlorine. This is 2 and that's 3. So let's see. 5.1 mole of chlorine. Right? 72. Ammonia reacts with oxygen to form nitrogen dioxide and water. We've seen that one before. You react ammonia and oxygen, and at the end of the experiment, you find that you produce 23 grams of water and have 8.52 grams of ammonia left over. What's the mass of oxygen reacted? Okay. All right, let's write the equation up there. For ammonia plus 7 oxygen yields 4 NO2 and 6 water. Okay. Let's see. You produce 23 grams of water. 23 grams produced. And have 8.52 grams of ammonia left over. 8.52 grams remaining. Okay. What's the mass of oxygen reactant? This is what we call blue smoke. You don't need to know that. All you need to do is convert this to moles, find out how much oxygen in moles that is, and convert moles back into grams for oxygen. This is superfluous. Now, if we asked a different question, how much ammonia was used, well, then we wouldn't need to know this either, but how much ammonia did we start with? That would be required this value. But since the question is here, we don't need to know that. We just need to convert 23 grams of water into moles, 18.02. And that's 1.2764 moles of water. Then we convert water to oxygen with 7 here and 6 there. And that's 1.489 moles of oxygen. Then we convert oxygen back to mass, 32. 47.7 grams of oxygen. Okay. This is a perfect example of one of the primary purposes of a word problem, and that is to confuse the reader. If the reader's not confused by the word problem, that means they know it pretty well. They know what needs to be used to find the answer and what is extraneous material. 73. For the reaction, C2H4, which is probably ethene, plus oxygen yields carbon dioxide and water. 5.5 moles of carbon dioxide are produced. How many moles of oxygen were reacted? All right, this is really simpler than we've had before. C2H4 plus 3 oxygen. And I'm leaving out the gas because all of them are gases. And 2 water. 5.5 moles of carbon dioxide produced. 5.5 moles produced. Okay. How many moles of oxygen were reacted? All right. This is really simple. CO2, oxygen was 3 here and 2 there. So we need 5.5 times 3 divided by 2. 8.3 moles of oxygen. Rounded off to 2 significant figures. Ooh. Now, why does it say 8.2? And I got 8.25. 5.5 times 3 divided by 2. Yeah, I got 8.3. So 8.2 is close, but since none of these is in there, you could say none of these. Now there's a chance that I might mark it wrong, but you're within your rights to come back and show me your work and say, I calculated 8.3 and that answer's not in there. Right? Then you would be justified for getting to get credit for that problem. 75. All right, consider the following unbalanced equation. Oh, we balanced this one before. We're gonna have to do it again. I guess so. C2H5, C2H5OH plus oxygen yields CO2 plus H2O. Okay, so let's balance it again. Should be able to go fairly quickly this time. 2, 6, and 2, 3. Be sure I got everything up there. Yeah, okay. On this side, 1, 2, and 3. Okay. We'll start with carbons. The 2 here. And that changes to 4, 5 oxygens. Okay. And then hydrogens, we need 6 on that side. Like 6 here, and that's 3 plus 4 is 7. Okay. Now we can put 7 halves and give us 7 there. And then we can get rid of the fraction. 2 here, fraction's gone, 4 and 6. There we go. So now we got a balanced equation. What do we do with it? 1.86 grams of ethanol. 1.86 grams of ethanol reacts with 14.3 grams of oxygen. How many moles of water are produced? So we're looking for moles. We're given exact amounts for the reactants. That means one of them is going to run out. So I'm going to convert this to moles and that to moles. So 1.86 grams of ethanol converted to moles. We need 2 carbons. We need 6 hydrogens. And 6 hydrogens, 1 oxygen. Yep. 6. I get 4608. 46.08. Divided into 1.86 is 4.0036 times 10 to the minus 2 moles of ethanol. And I'm going to go ahead and convert that to water so I can compare the oxygen value. So this is ethanol is 2, cancels that, and 6 water. So I just need 3 times that value. So I get 1.21 times 10 to the minus 1 moles of water. Then we'll do the same thing for oxygen. 14.3 grams converted to moles. Oxygen is going to be 32 grams. 2 times 16. .469 times 10 to the minus 1 moles of oxygen. Then we'll convert oxygen to water. And oxygen has 7 here and 6 there. So that gives me 3.83 times 10 to the minus 1 moles of water. So which one's limiting? The smallest one. Right? The ethanol produces the least amount. It's probably, yeah, it is. 1. Yeah. Move it 1 to the left. 121 moles. There we go. So that's E. All right. Skip a few. Time for this one, number 80. Uh, 22.5 grams of nitrogen and 22.5 grams of hydrogen. Determine the mass of ammonia that can be produced from these 2 reactants. For this one, you have to know that nitrogen reacts with hydrogen to produce ammonia. And then you have to balance the equation. 2 there, 3 here. Then if you're given 22.5 grams of nitrogen and 22.5 grams of hydrogen, the mass of ammonia then would be dependent upon which one is limiting. So we'll take 22.5 grams of nitrogen and convert it to moles. So that would be 28.02. Just add it up. 2 times 14.01. 22.5 divided by 28.02 is 0.8030 moles of nitrogen. And we're going to go ahead and convert that to ammonia. So this is 2 and that's 1. So 2 times that, which is 1.61 moles of ammonia. We'll do the same thing for hydrogen. Two times 1.01 is 2.02 grams. Which is 11.14 moles of hydrogen. I think I can see where this one's going. So this is hydrogen cancel and give us ammonia. This is still 2 and this is 3. So 2/3 of that would give us 7.43 moles. So there's your limiting one. Now we just have to convert it back to grams. So what's the molar mass of nitrogen? 14.01 plus 3.03 for the hydrogens. 1704. So let's flip this one and 1704. I get 27.4 grams of ammonia. Yeah, it would be B. Right. Three. We're running down to the wire here. Let's see. Fe2O3 reacts with carbon monoxide according to this reaction. When 470 grams of Fe2O3 react with excess carbon monoxide, number of moles of iron produced. Okay. So this is 83. And our equation is Fe2O3 plus carbon monoxide yields 3 and 2. Okay. 470 grams. Fe2O3 and excess carbon monoxide. Okay. And the question is number of moles of iron produced. Okay. So what we need is molar mass of Fe2O3. So we need 2 times 5585 and 3 times 16. $159.7. Does that make sense? Yeah, this is 48 and that's over 100. Okay, that's good. So we're going to convert 470 grams of that reactant into moles. 159.7. I get 2.943 moles of Fe2O3. Now we need to convert moles of iron. So iron's on top, Fe2O3 on the bottom, which is 1 and 2. We're rounded to 4 significant figures. 5.886 moles of iron. That would be C. All right, 84. Okay. Which of the following statements is always true concerning a reaction represented by the following balanced chemical equation? So that's 2 ethane plus 7, there should be a plus sign in there, plus 7 oxygen yields 4 carbon dioxide plus 6 water. Let's see. Well, since A says none, we'll leave it to last. How about B? If we have an equal number of moles, oh, okay. We need the equation. 2C2H6 plus 7 oxygen yields 4 CO2 plus 6 water. Okay, we've got multiple comparisons in here. Equal number of moles, different number of moles, equal masses, more mass of one than the other. The question is, which is limiting, or is there a limiting reactant? So in order to tell that, I would go for comparing stoichiometric ratios first. So a stoichiometric ratio here, if we say C2H6 and oxygen, those are where we're focused. Stoichiometric ratio, let's see. This is the stoichiometric ratio for moles. Okay. What would be the stoichiometric ratio for mass? We would have to convert 2 moles of C2H6 into mass. So that would be 2 times 12.01 and 6 times 1.01. Okay. And that would be 30.08 times 2 would be 6.02 grams. 6.02 grams. And then we'll compare that to 7 moles of oxygen. And that would be 32. So 32 times 7 is 22.4. 22.4 grams. Okay. These are the stoichiometric mass ratios. This ratio of 22.4 to 6 would be exactly the right amount. So now we can go to our questions and say, for B, if we have equal number of moles of C2H6 and O2, there's no limiting. Well, equal number of moles, one of them would be limiting because they're not equal. It's 2 to 7. So if we had 2 moles each, then oxygen would be limiting. If we had 7 moles each, then, well, oxygen would still be limiting, right? So B can't be it. That's a false statement. If we have equal masses, there's no, well, equal masses, the equal masses would make one of them run out because the ratio is 6 to 22. So C can't be it either. If we have more mass of oxygen than C2H6, more mass of oxygen than C2H6, more mass of oxygen, then C2H6 must be limited. You can't say that. Because if you had more mass of oxygen, you could have 7 grams and oxygen would still be limiting. Right? So we can't use that statement either. E says more mass of C2H6 than oxygen limited. Yes. If you have more C2H6 than oxygen is definitely limited. E is your answer. I think that's it. Yep. Okay. So just a reminder, this is Tuesday, next Thursday, I'll be here I'll be zoomed in for about a half hour in case there are any questions, because the exam's not until a week from today. I'm pretty sure. Yes. Tuesday, March 25th is the exam. So next Thursday will be question answer. If nobody shows up to answer questions in about 30 minutes, I'm going to cut it off and go do something else.